Professor Stache completed her undergraduate work in chemistry at the University of Wisconsin-Green Bay, after which she started her graduate studies at Colorado State University. After completing her PhD, she did postdoctoral work, some different fellowships, and we are very excited that she is now in Princeton, so right down the road. But thank you so much for joining us tonight, and we are excited to learn more.
You're welcome. All right. Well, thank you so much for having me. Yeah, it's fun to be a part of this lecture series. I'm sort of interested to see what all the other topics were, and maybe some of this will be review. But it'll give you a little bit of a flavor for a lot of the commercial plastics that we're using today, so maybe it'll be a lot of review. And I'm also going to talk a bit about our research. So not all doom and gloom, but what we are trying to do as academic researchers to try and combat the plastics waste crisis. So as this sort of depressing video shows us, and we all can see as we walk around outside and as we drive along the roads, we can see a lot of plastic waste building up in the environment. Plastics are, they completely revolutionized our modern society since their inception, probably back in the early 1930s, really making commercial production around the 1950s. And we wouldn't be here today. We wouldn't have the technology we have today without plastics. We wouldn't have some of the efficiencies and things that we depend on every day without plastics. But it comes at a cost, as we are starting to definitely realize and now reconcile with. So first of all, what is a plastic? And you may already know this, maybe this is just recap, but plastics are made up of repeating small molecules. So when we refine oil, we get these really small molecules that you can put in a reagent bottle. And when we apply a stimulus, all these molecules can be connected together to make these really long chains. So you could almost imagine this as being like little popcorn kernels, right? When maybe you decorate your tree and during the holidays, start with a single kernel of popcorn and you string them all together. That string would be like what a polymer is. And it behaves differently than just a single kernel, right? They're all together. They can start wrapping around each other, which would be very problematic if you're trying to decorate your tree. But for polymers, and plastics in particular, this is actually a really important property. And so they can be, all the same length, like the ones I just showed. They can be all these different lengths, and this will change the type of properties that you can get. So you can imagine starting from exact same molecule. So say it's ethylene, just 2 carbons put together. And you can make a whole host of different properties depending on what these chains look like. So for example, both of these plastics up here, this milk carton versus this, what was a nice New York Times plastic bag and now is sort of destroyed, these are both made from the same monomer, but they are very different polymers in the way that they're constructed. So this one you can see has sort of hard sides, it can easily hold milk. You can't really mold it very easily, whereas this one is very stretchy. And if you tried to put milk in here, it may not hold it and it may start to leak over time. And of course, you all know that we have plastic surrounding us, plastic water bottles. Our clothing is often made out of nylons or polyesters. Those are plastics. Our food containers, toys, Legos for kids. A lot of our cars and automobiles or other transportation is made out of plastic or plastic composite materials. A lot of our medical equipment, this is actually really important for medical innovations, that we have this disposable, sterilizable material that we can easily use to allow for medical treatments. And of course, adhesives, right? How do we stick everything together? Glues, epoxies, maybe you used these before. These are all made out of different types of polymers. And so, is anyone familiar with these RICs? I'm sure you are after you've been sitting through this seminar series, right? Having all the different little recycling triangles on the bottom of the containers. And so up here, I have all 7 of the RICs that we have. One, which is polyethylene terephthalate. So one example of this is not what is inside this container, but a Tide Pod container, right? This is made out of polyethylene terephthalate. If you look at the bottom, although in this one it's really hard to see, you can see that it has a little number 1 on it. The 2 that I showed you before, the plastic bag and the milk carton, these are both made out of polyethylene, but because they're so different in how they're put together, they actually get 2 different resin identification codes. So this one is number 2, and this one is number 4. You can see I have them in the same box up here. Number 3, I could not find my PVC pipe sample, unfortunately, but I'm sure you've all seen PVC pipe, right? That's made out of RIC number 3, and so is this cute little rubber ducky. I don't know why it's made out of PVC, but it is. I'm sure a lot of you have used Tupperware before. This is RIC number 5. It's a great plastic. It's really good for storing our our food, so we can keep them for a long time in the fridge. And Tupperware lasts a very long time. I know if I go to my mom's house, I will see Tupperware that's about 40 years old. And so it is a very durable plastic. I have up here some coffee cup lids. So these are all made out of number 6, which is polystyrene. Styrofoam would be the most common plastic that you would see, right? That really somewhat annoying packaging material. It's great packaging material, but it does get kind of flaky and get everywhere. And then number 7 is the catch-all. So this is all other types of plastics. So this would include polyesters, excluding PET. The other types of polyesters, it includes PLA. So if you liked iced coffees, that often comes in a PLA cup. This is also a PLA container. I think this maybe housed chocolates or something before. Sushi, this was a sushi container. Okay. Polymethyl methacrylate or plexiglass, so windows, that would also be RIC number 7. It's basically the catch-all category for everything. You have a question? The PEP? Polypropylene. Yep. Yeah, so polyethylene terephthalate, polyethylene, polyvinyl chloride, sorry, I should have said these, polypropylene, polystyrene. This is just one example of number 7, PLA, but it can be a lot of other types of plastics as well.
The PET and PE, is that polyethylene
Terephthalate. Mm-hmm. Yep, so it comes from this structure right here. This is called terephthalic acid. And so it's a dicarboxylic acid, if you know what that is. But this piece right here, and that's where the name comes from. Yep, yeah, and then the ethyl part is from ethylene glycol, so that's often the comonomer. So you take terephthalic acid and ethylene glycol, you get polyethylene terephthalate. Mm-hmm.
I've seen a number of objects that have the little triangular shape but no number in them. What does that mean?
Nothing. So the interesting thing about this little triangle is RICs don't really tell you much of anything. All they tell you is that this container contains some amount of PET resin. That doesn't mean that it's only PET, and it certainly doesn't mean that it's recyclable. So unfortunately, it seems as though back when these RICs were being made, that part of the purpose of them was to indicate that the materials might be recyclable and perhaps fool the public onto their ultimate recyclability, which unfortunately is not necessarily the case. So all these RICs tell you is that it has some amount of that polymer resin in the plastic. Oftentimes it has a lot of other materials. So this Tide Pod container, for example. Very nice, right? Very good container. You go pick this up at the grocery store or convenience store, and you can take it home and you can wash all your clothes. It says it's RIC number 1. It says PET, so it does contain some amount of PET. I would imagine that this container, at least the body of the container is made out of PET. I'm not sure if this top part is actually made out of PET. It seems slightly different. But PET is not orange, right? PET is a colorless, I don't have any colorless plastic up here. Water bottle, that's PET as well. PET is clearly not orange. So where is that orange color coming from? It's coming from some dye that's added to give it this aesthetic property so that you know when you're buying the orange container, it is a Tide product. The label is also not PET. This is most likely some sort of vinyl polymer. So it could be PVC or it could be some sort of polyester. I'm not entirely sure what this is made out of. Obviously it has paper-like quality, a paper-like feel, but it's not actually paper, it's plastic. And then the adhesive. There's something that is adhering this label onto the plastic container itself. That is another type of polymer that has different properties than the label, than the container, and the orange dye is likely a small molecule. So this is RIC number 1, but there's a lot more in this plastic container, right? It's not pure polymer. And that's one of the problems that we have when we're dealing with plastics recycling. It's not just a pure single component, right? If we take that water bottle that Hanning was, that's a great, I might steal that from you. If you want to recycle that, that is pure PET. That's all that's in there. This would be very easy to melt down, chop it up, and reprocess it, and you would just get the same water bottle out, and it would be great. Problem is, if you melt this down with this, now what are you going to get? You're going to get some mixture of orange material, and then whatever additives may be in this would be incorporated into this water bottle as well. That's one of the challenges, and these are just a few examples of plastic, right? You've all seen hundreds of different types of plastics.
Since they're all
They are not. So I'm going to talk about what specifically is recyclable in this county, at least what I interpret the website to tell me.
We actually brought the little magnets that tell you what you can and can't recycle.
Does it tell you the numbers by chance? Because I was looking on the website.
This is some of the numbers are misnomers and so that.
Okay.
They're moving away from numbers.
Yeah. In Middlesex County, they're trying to move, because they said the number doesn't.
Yeah, this is what I
line
have
up
later.
number.
Okay.
That type container is clear, would it be recyclable?
So I think, so they will tell you, this is something that you can put in the recycling here in Middlesex County. So this type of container, this milk jug, not Tupperware containers, but other polypropylene can be recycled. Number 5 is typically recycled. So bottles, jars, jugs, tubs, those types of things can be recycled. These plastic bags and grocery bags cannot be recycled. Number 4, low-density polyethylene is not recycled. So, am I going to get to that? Yes, right here it is. Perfect. Yep. So the plastics that you can recycle, it's going to be likely number 1, number 2, and number 5, although I don't think you can recycle Tupperware. I don't think that's one of the things you can recycle. 1 and 2. Okay, so maybe number 5 isn't part of it.
They're trying to do this initiative of like the bottles, jars, jugs, tubs.
Yep.
They're trying to-
Yep.
We have recycle coaches, Brunswick, so they can find out what's recyclable.
Oh, that's great.
So you
That's
take what you
fantastic.
have, and it will tell you if you can put it in your single line waste, in your container at home, or if you have to take it to a store or other facility.
Yeah, that's fantastic. I mean, that's really helpful, especially if they have a triangle and it doesn't have any information in it, right? Like, I have some sense of what these plastics might be if they don't have the actual number on it, but for you as a consumer, right, not an expert who's constantly thinking about polymers or plastics, you may not have that appreciation. So in general, it's number 1 and 2. In Mercer County, we can also recycle number 5, but it sounds like maybe we can't do that here. Which unfortunately means that styrofoam, if any of you are planning on Black Friday shopping, getting like a big TV, get a lot of styrofoam packaging material, unfortunately it should go in the trash unless there's a styrofoam collection. All right, there you go. Unless there's a styrofoam collection center, then you can take it there. But it should not go in the standard commingled recycling that you're typically using on the curbside. Yeah, and including like all these different lids, your coffee cup lids and your coffee cups, not recycled, unless they're made out of PET. So you can look on the bottom and see if it says it's a number 1, then you could throw it in the recycling because it's just like this water bottle. But if it's a number 7, then it's PLA, which unfortunately is not currently recycled. So there's a lot of plastics I showed you that are not being recycled, right? And of course there's other materials that are not, yeah.
So they are collecting styrofoam in the recycling center. Does that mean that it's actually being recycled? Or it's possible to recycle?
I'm not entirely sure what they're doing with it. There are a few polystyrene recycling, I should say pyrolysis plants throughout the country. I'm not sure if that's what they're doing or if they're trying to repurpose it. They could be trying to repurpose it, which is a form of recycling, and that's not a bad strategy. Styrofoam obviously can have limitations because it can break down pretty easily. Or they could be compressing it and turning it into some other type of plastic. Compressed, okay, there you go.
And I was going to say, years ago, and I can't tell you how many years ago, but I know that stores like UPS stores, those stores used to take your like popcorn styrofoam. They would take it because then they would reuse it for their packaging.
Sure, yep. Yeah, it's definitely something that you can reuse. I mean, I'll have like a little bit at the end of like things you can do at home. But that's definitely one option that we can sort of reuse plastics. It usually doesn't have an infinite life cycle where you can keep reusing it forever, but you can definitely give it multiple lifetimes, which does cut down on the amount of plastic for sure. So just pay attention to this, make sure that you're putting in the appropriate things into the recycling bin. And unfortunately, if it shouldn't go into the recycling and there's no other collection facility in the area, it should go into the trash and it will get landfilled. And while that doesn't sound great, landfilling the plastic is a way of maintaining it. It's not recycling, but it is a way to appropriately manage it such that it's not necessarily getting out into our ecosystems. So what is plastics recycling? The ones that we do recycle. There's two different ways that we typically recycle it. We can reuse it, of course, which is reusing, not recycling. That is one way to reprocess it and give it a second lifetime. The most common method for plastics recycling, so for number 1 and number 2 and number 5, is mechanical recycling. And so when I said we could take this water bottle, we could chop it up into small flakes, you can melt it down, you can blow mold it to get back to the same structure. That is a way to recycle it. That is mechanical processing. You can cut up the plastic, melt it down. Most of these will melt at pretty modest temperatures, and you can formulate it into a new material. This works really well for PET, it works really well for high-density polyethylene, and it works really well for polypropylene. It's not an infinitely repeatable process, because when you start chopping up these plastics, remember how I showed you those long chains at the beginning? Over time, you're going to start cutting those chains down, and as you start cutting those chains down, you start to lose your properties. So it's not something that you can do forever, but it is a way to give it multiple life cycles. The main challenge with mechanical recycling, and we're pretty good at this now, you throw everything in the same recycling bin, right? We can sort the plastics pretty efficiently in the recycling centers. So that's great. They can separate out this plastic from this plastic using their sorting technology. If they didn't sort them and you tried to mix these together, you would get a very low value product at the end. It would likely be brittle, it would be inhomogeneous, it might be like an oil of water situation where you have pieces where it's PET and then you have other pieces where it's high density polyethylene. And that's probably not a plastic that you're going to want to use for these same applications. So mechanical recycling, very cost effective, easy to collect, chop it up, reformulate it, you get to the same products. Chemical recycling may be something else you've heard of. And chemical recycling can take many different forms. It's basically applying some sort of chemical stimulus to the plastic to transform it either back into those monomers that I was talking about at the beginning, so you can keep making more and more plastic, but now you have a closed loop cycle. So you start with your monomers, you make your plastic, and then you chemically recycle it back to the monomers. You just keep doing that cycle, and that is infinitely reprocessable. Right? If you get back to the starting building blocks, you can keep making the same material over and over and over. The problem is this tends to be very energy intensive, and so chemical recycling really only works for PET right now. Yeah. So what does this mean? This is sort of the scary picture, some of the scary stuff I'm going to tell you about now. Most of our plastics come from oil feedstocks. Oil is very cheap. We're able to refine it, we're able to get our molecular building blocks, our monomers, and we can very cheaply convert it into all of these different plastics. And this is a good thing, right? Because if these materials were very expensive to make, that means the cost of goods would go up dramatically, right? There's a reason we've kind of moved away from things like glass for housing some of our materials, and it's because glass is very expensive to transport because it's so heavy. These things are very lightweight and they're very cheap to make and they're very durable. They're not going to break. You can throw this against the window as much as you want. It's not going to do anything. It's totally stable. So that's the good side. The bad side is we produce hundreds of millions of metric tons of plastic every single year, many of the ones that I've talked about, and we recycle less than 10% of all the plastic we produce. So we're increasing production quite dramatically, and yet we're not increasing the amount of recycling. Now, there are other ways to manage plastic waste. So like I said, landfilling, although no one wants more landfills going up in their backyard, obviously, it is a way to manage the plastic waste. And over hundreds of years, that plastic will start to break down through natural processes, and it will turn back into carbon sources that we could harvest again to make more materials. It takes a long time, so it's not really on the time scale that we're talking about, but it is a way to manage it, just to bury it. We can also incinerate the plastic, so burn it. Obviously, this generates CO2, so we need to think about how we capture that CO2, so we're not putting more of that into the environment. But it is a way to harvest the energy from the plastic and get rid of some of the plastic waste buildup. The bad part and the problem that we're really worried about is this environmental leakage. And this is what you see along the roadside. This is what you see building up in waterways, in natural environments. Any of you have heard of Trash Island out in the Pacific? Yeah, this is a huge island. I think it's greater than the size of Texas now, that is just filled with plastic trash. and other trash as well. I think 90% of it is plastic waste. So we're now making islands out of plastic. Now the scary thing is we're making a lot of plastic. Plastic production has been ramping up significantly. And so think about all the plastic waste we have right now. That's expected to double in the next 25 years. So we've been making plastic since 1950. Granted, a lot of it has been in the last 4 decades or so, but it's supposed to double by 2050 because our plastic consumption is continuing to increase. You can see here from this graphic, we've produced, 8,000 million metric tons of plastic up until now? Yeah, somewhere along that line. Or we generated that much waste. And this is where it's supposed to be by 2050 of all the plastic waste that we're going to generate. So this is a major problem of all the plastic we're generating. And if recycling doesn't manage this, if we're still staying at this less than 10% rate, that plastic waste is going to build up in the environment. Some is going to be landfilled, which is okay, but a lot of it is clearly escaping. And so this is a challenge. To give you a sense of the volume of plastic that we're talking about, this is a nice graphic, actually from quite a few years ago now. But if we imagine that 1.3 billion water bottles are produced in a single day. That volume of plastic is mapped here next to the Eiffel Tower. So that's a lot of plastic. Now we think about all the water bottles produced in 10 years, that's 4 trillion bottles. That is a mountain over Manhattan. So just thinking about the amount of plastic, because I say millions of metric tons, what does that mean? This sort of gives you a sense that this is just water bottles of how much plastic we're producing. It is a lot, and a lot of it is single use. These water bottles tend to be single use, right? We use them, we throw them in the recycling bin. And if it's not a water bottle, but say it's a milk jug that doesn't get recycled, or it's these plastic bags that don't get recycled, then these have to end up somewhere, right? They're gonna end up in the environment, or they're gonna end up in landfills. They're probably not gonna be managed properly. And this is Trash Island that is currently growing. Estimated 1.8 trillion pieces of plastic, and of course more of it is starting to aggregate and continuing to grow. Now people are trying to retrieve some of this plastic and take the pieces that they like and that they are recycling, but obviously it's going to take a long time to try and shrink down this island. So back to the scary video, which shows all of the plastic waste in the environment. I actually saw something similar to this. I'm an avid runner. I was running along the towpath in Princeton, and for a while they were working on some of the bridges in the town, and they had dredged up the river a little bit, or the canal, so they could work on the bridge or whatever. And I was running by, and it was just, when you dredge something up, you have all the sediment sort of collect. It was just filled with plastic. I was like, oh my God, we need to get out there and pick that up, right? Like, this is just not good. And of course, this is happening all over the world. So what are the solutions? Now I'm going to tell you about some of the bright spots and tell you what we in my research lab are trying to do and what a lot of scientists around the world are really trying to do to help fight this crisis. We basically have a linear plastics economy right now. We start with oil, and unfortunately most of it ends up in the trash or it ends up mismanaged in the environment. And so in my lab, and in many labs, we try to think about making new polymers that are maybe inherently more degradable. So things that could mimic the same properties of these commercial plastics that we know and love and depend on, but maybe they are either easier to recycle, or if they end up in the environment, they can break down on a much faster timescale. They won't produce microplastics, and hopefully they will degrade into, especially if they come from biodegradable or biorenewable sources, they'll break down into non-harmful components. There's a lot of research going into this area. It takes a long time to get a plastic online. So PET, when was this discovered? Back in the 70s? Something like that. This plastic, which PET is very commonly used now, right? You see PET everywhere. And it's great because PET is actually recycled pretty efficiently. I think it's greater than 30% of PET is recycled. So if you want to prioritize buying a plastic, look for RIC number 1. Use water bottles that are made out of PET because it is more recyclable. But it took decades to get this plastic online. It takes a long time to bring in new materials. In this case, the monomers are very cheap, and so that's great. But some of these new plastics that we're trying to design, perhaps the monomers are more expensive to mimic the same properties or to become biodegradable. And so it takes a lot more time to bring these online. So you have to spend a lot of R&D into developing them. And unfortunately, it could also mean that they become more expensive products. So that's always a downside of making plastics that could be better for the environment or better for humanity. But a lot of the work that we do in my lab is really focused on the plastic waste that's up on this table. We try and develop ways to, if you think about this plastic essentially as valueless after you use it, right? You buy the container, what happens to it? If it's not recycled, it becomes trash, it has no worth. We try to find value in these products so that we can develop processes so that people will take these into their process and perhaps get a high value product out. Maybe it's the monomer, maybe it's something else, but something that they can make a business on so it can actually incentivize recycling and promote good recycling practices. So that's what we do a lot of in my lab. We work with the post-consumer waste that I have up on this table, and we try and develop really unique, economic, effective strategies for recycling. And we have spent a lot of time on polystyrene in particular. I wish I had styrofoam up here because it's the best example, but we work on these too. So we think about styrofoam because it's poorly recycled, so less than 1% of it is recycled. In some cases they are reusing it, right? Maybe compressing or turning it into something else. But it's a huge market, and it's a great product, right? There's a reason we use polystyrene foam. It's very lightweight. So you imagine you're shipping your TVs from overseas, right? You start using a heavier plastic or something that costs a lot more money, that's gonna increase the cost of the product that you're buying. And so that's one of the values of using such a cheap, lightweight, durable plastic. But unfortunately, people don't like it because it does take up a lot of space, right? So when we say landfilling is an option, that's great, but it fills up 1/3 of the world's landfills because most of it is air. So you can compress it, and then you can landfill it, and then it's smaller, and that's okay, but you do have to collect it to do that. So we really think about post-consumer waste. All of this came from oil, right? We refine the oil, we have crude oil, we refine it into monomers, we make polymers, we make plastics, we make products. And once we're done with this and we throw it into landfill, we've lost all that value. So what we want to think of is waste plastic as an initial oil feedstock, that carbon value that we had, that we turn into a product. How can we exert value from this waste plastic? And so we've thought about doing this using some of our chemistry. I'm not going to go into the details here, but we can turn it into these small molecules. So these are similar to the monomers. And these have their own markets. So this is benzoic acid, sodium benzoate. You might have heard of this before. It's used as a preservative oftentimes in sodas and other foods. It can also be used to make fragrances. It's a good precursor for esters, which smell really nice. Or acetophenone, which can also be used as a fragrance precursor. So you can see these are much smaller than polystyrene, but it is a way to exert value from this waste plastic. Larger potential pathways would be this compound over here, which is called phenol. So maybe you've heard of phenolic resins. It can also be used in some epoxies or sealants. This is a huge market, and this market is increasing in value. It's going to increase in size. And so this would be a great product to try and access because it doesn't come directly from crude oil. Benzene comes directly from crude oil, so even though it's a huge market, converting polystyrene into it likely isn't the best pathway. And this pathway here, this is the monomer. This is the building block for making polystyrene, for making styrofoam. It's a huge market. It can also be used to make other things. And this pathway would be chemical recycling to monomer, where we have that closed loop recycling. And so what we really try and do in my lab is take our understanding of fundamental chemistry, apply it to these products to make these different molecules in very selective ways. So maybe we get a single molecule out, and we can access these products, these value-added products. So one thing that's kind of interesting is plastic does break down in the environment. And one of the ways it does this is through photooxidation. So sunlight, right, gives us a lot of energy. All of that light is energy in the form of photons. And we also have oxygen. So we know that oxygen is a very good oxidant. It's good for fires, right? It's what makes fires grow and breathe. And so in this case, the combination of sunlight and oxygen with a plastic means that it will start to break down over time. We'll start to oxidize the backbone of the polymer. If you've noticed plastic out in the environment, it gets kind of yellowed, right? That's because it's starting to break down, it becomes brittle. That's what's happening. It's starting to get oxidized, and it's starting to break down into smaller pieces. And once you get into these smaller pieces, then perhaps some of the bioorganisms in the environment can break them down into useful building blocks that they can use to grow. This process takes a very, very long time to get here. This will take hundreds of years. And so what we wanted to do is accelerate this process in the laboratory and get this particular product out so that we could add that value-added product from polystyrene. So we used some of our creative chemistry. We're using this iron. This is an iron complex. It's dirt cheap. It costs essentially nothing. You could actually probably use dirt and mix it in with the plastic and it would do the same thing. We use a little bit of oxygen, so just using air or an oxygen balloon. And it turns out we can take this post-consumer waste, so we can take styrofoam or this little lid, and when we expose it to these conditions, we can convert 50% of that, so 50% of that mass, into benzoic acid. So now we've turned something that was worthless into something that has value. Now we have benzoic acid, and we can use that perhaps as an additive, or sodium benzoate. So sodium benzoate, yeah, you can buy this in the store, I think. We can turn it into that, or we can make it into acetophenone, which could be used as a fragrance. I'm pretty sure it doesn't make Chanel No. 5, but that's the sort of thing that we're trying to do, right? Can we take these products, can we take these waste products using our chemistry and start to feed them into these high value product streams to create value and recycling incentives? So basically we take all of our long chains, our waste polystyrene foam, we expose it to light and a little bit of other dust, and then we can get these products out pretty easily.
Sodium benzoate, isn't that added to food as
Yep.
a preservative? So
Yep.
we're actually eating plastic.
So this is not the way that sodium benzoate is made. This is just a proposed way. So what I want to clear up is that it doesn't really matter where it comes from. So sodium benzoate, if it's occurring naturally or if it's made in a lab, what it's made from, it doesn't really matter. As long as it's purified to the same extent purity, it's the exact same compound. So even if it comes from plastic, it's the exact same thing. I know it sounds scary, but trust me, it's the exact same thing.
So occurring naturally, we eat it also sometimes.
I'm not sure if I'm assuming there's natural sources of sodium benzoate. No? I don't know. Sorry, I'm looking at my student in the back handing. But we can get aspirin from naturally occurring sources, or we can make it in a lab. It's the exact same thing, as long as it's purified the same way. So the impurities that could come along with it are something you want to be concerned about. But if it's purified to the same, like 99.99%, it doesn't matter. It's the exact same thing. It's made up of the exact same elements. It doesn't really matter where it came from, if it came from a natural process or a man-made process. It's a great question, and it's kind of scary, right? Because you're like, I don't want to put this in my body, right? But this isn't what you're putting in your body. You're putting in that same compound, regardless of where it comes from, as long as it's purified to the same extent. And so, one of the things that we really focus on in my lab is applying our chemistry to post-consumer waste, which is kind of nice because our starting materials are very easy to come by. I can go get coffee and I can give the lid to Handy and then she can break it down in the afternoon. So that's kind of nice. But it's important to test and validate our chemistry on post-consumer waste because like I told you, this isn't pure polymer, right? There's a lot of other material in this plastic that we have to be worried about. And so we want to make sure that our process will still work even if it has all of these other additives. So that's one thing that we're doing, and we have a lot of ideas on how we can maybe increase the market size of some of those products. So one really interesting collaboration that we have with another university is sodium benzoate is a feedstock for some biomolecules, or some bioorganisms, I should say. And they can turn sodium benzoate into another polymer, into a biopolymer, which you could then use for another application. And so it's not just a sodium benzoate intermediate, but can you feed it into another downstream process so you can get value, make another high value product. That's one thing we're thinking about. The other big focus of our lab is chemical recycling to monomer because it is this closed loop. You have this infinite recyclability. Now, there's a lot of challenges with this, and the biggest one is that it's highly energy intensive. So the really interesting thing about polymers, and all the polymers that we have, there's a reason that we use these plastics. And I have essentially these 5 plastics probably comprise what, 80%? Probably 80% of all the plastic we have, just these 5. We make a lot of polystyrene, fine, these 6. 1 through 6 comprise like 80% of the plastic that we have. And they come from the same building blocks. And the reason is 1, because they come from oil, so they're very cheap, they're easy to get their hands on. But 2, they're very easy to polymerize. So if you have the building blocks, you can basically just give it a nudge and it's gonna fall down a hill and it's gonna make the plastic. It takes very little energy to make a plastic. The problem is, so if we have our monomers, say like we're right here, we give a little stimulus, goes up the hill, it goes way down here. The problem is if we want to get back to our starting point, we have to go over that same hill that we just fell down. So imagine you start close to the top of a mountain and then you go all the way down, but you need to get back up to the top. That's the problem. It takes a lot of energy to climb back up that mountain. And that's the problem that we're facing with plastics recycling. It takes a ton of energy to reverse the process to turn it back into monomers. And so if you have the option of spending a lot of money to reverse the process or just buying more oil, you're gonna buy more oil because it's gonna be cheaper. That's the problem that we're facing. So what we try and do in my lab is find cheaper, more energy efficient solutions to recycle these plastics. Now, like I said, polystyrene is recycled, and the common way to recycle it is through pyrolysis. It's very small, not much of it exists because it's so energy inefficient, but it can happen. And so in pyrolysis, we want to start breaking down that polymer. We need to heat it to greater than 750 degrees Fahrenheit. So imagine you're making your turkey for Thanksgiving. If you put it at 750, that thing's going to be toasted really quickly, right? That's a lot of energy. It takes a lot of energy to heat up that plastic and convert it back into the monomers. And this is the problem with plastics recycling. So pyrolysis versus incineration, because sometimes these terms get confused. So in pyrolysis, if you heat the plastic, whatever your heating source is, say you're using fire, and oxygen is present, you're going to incinerate the plastic. You're going to turn it into carbon dioxide, H2O, and carbon soot. You're going to get char out, right? This is when you cook a burger too far and it starts turning black. That's what's happening. You're incinerating it. And this is one way to recycle polystyrene, but this is not pyrolysis. Pyrolysis, if you heat the plastic without oxygen, you just start breaking it into smaller chains. And so you get these little, we'll say, reactive species, so they're very high in energy and they don't want to sit there. And they start to break down further with more heat, and you start to get back to the monomers. So pyrolysis and incineration are 2 very different things. They both involve heat, but one is with oxygen and pyrolysis is without. And so pyrolysis is the process by which we recycle polystyrene. Like I said, 750 degrees is a lot of energy.
How would you heat it without oxygen, or is it in it like an oven?
So the way they do it is under inert gas. Yeah, so most of our atmosphere is actually made out of nitrogen. It's only about 20% oxygen. 20% is definitely enough to incinerate. But if you clear out our atmosphere from all the oxygen and you just use nitrogen, it will not burn anymore because nitrogen is pretty inert. Yep, exactly. So they just use like a constant stream of nitrogen pressure to make sure that the oxygen isn't there.
Pyrolysis is the problem with microwaving your food and stuff and plastics?
It doesn't get hot enough to actually do this process. It can heat up. Yeah, it doesn't. Microwaves will not heat the plastic hot enough to undergo this pyrolysis process.
So that brings up the second question. Where are all the little microspheres that we're all dating all our bodies coming from?
The most common method is abrasion. So grinding. So, sorry, Hanning.
So there's no heat thing, it's just
Not, heat
small-
doesn't necessarily have to be
small
processed.
little pieces of polymer are coming out from abrasion.
Yep, abrasion is the most common method of microplastic formation. Don't drink this. Because every time you do this, it's coming just a little bit.
For a long time, because some of these microplastics go into the water.
So if this was in the sun for a long time and heat, then you would accelerate the process of photooxidative degradation. So the sun has a certain energy. the more energy you give it with the addition of heat can accelerate the process. It would start on the outside though, so it would take a little bit of time to get to the inside. But just the heat itself would not be enough to generate microplastics on the time scale that you're thinking about drinking this water. Yeah, you let it sit out there for a year, maybe you don't want to do that. But I think on the time scale you're talking about, it'd be fine.
So all the warning to not heat up with the plastic, they're not.
It's not, so it's not that it's going to pyrolyze it. But like I said, these are not pure, it's not pure plastic. There's additives. And those additives can leach out. Because when they make this plastic, so if you bought some PET plastic, say you wanted to buy it online, you could buy this from Amazon, you could buy PET pellets. It comes in little pellets. And those pellets can form this bottle. And the way they form it is they heat the plastic, it becomes moldable. So sometimes its viscosity is so low that you could actually blow into it like a bubble, and you could make a bubble, and then you let it solidify, and you have your plastic. So at some point, the plastic starts to flow, and whatever might else be with the plastic, so additives like plasticizers, can come out. And so when you microwave it, that is the concern. It's really the additives leaching out, not the plastic itself. The plastic is perfectly stable under microwave conditions. It's the additives that could be leaching out. So I do not microwave things in plastic. Now, yeah, that's all the further I'm going to say. I do not microwave things in plastic. I think it's just a general good idea. Use glass.
So even the microwavable container, plastic.
Microwave safe essentially means it's not going to deform. I don't know, Hannah, you can correct me if I'm wrong. I don't know how much of, when it says microwave safe or dishwasher safe, that it's talking about the additives not being able to leach out. I don't think that has been as extensively studied. So when it says it's microwave or dishwasher safe, it just means that it's not going to fall apart. It's going to retain its shape.
I'm just curious on how much toxicity is released into the air that we breathe in this process.
So if you did this on an open benchtop, that would be very dangerous. These are all done in controlled environments with the appropriate engineering controls. And so the product, the exhaust streams should be controlled, should be filtered. And so there should only be, steam or something coming off. The rest of it should be collected before it gets out into the environment. So all that would have to, of course, be regulated, but that is, the process. We do all of this work in a fume hood, so it's all being ventilated and exhausted and filtered. Yeah, you do not want to do this because you're absolutely right. These monomers are toxic. So it's sort of interesting, like you were concerned about the sodium benzoate. The individual components that make up these plastics would be toxic to you by themselves, but when they're in a polymer, they're perfectly stable and safe. It's like, they're not going to be giving off gaseous vapors or anything like that could hurt you. So, a lot of energy. Where do we get this energy from? Usually it comes from fossil fuels. We heat up coal, and we generate enough energy that we can induce pyrolysis. Now, of course, we have other ways of getting this energy. Why am I blanking on solar cells and things like that, right? We can collect that energy and use it. We're trying to increase the efficiency of those. But we look directly to the source. We're not trying to convert the energy into something else that we can use. We want to use the energy, the sunlight, directly. It's the most biorenewable source that we have. The sun is out there every single day, right? It's not going away in our lifetimes, so at least we're okay. And so we can use that energy. Like it's giving off, I don't have an energy estimate, but it's giving off a ton of energy every single second, and we can try and harness that. And so the process that we're trying to take advantage of is this thing called photothermal conversion. And I bet you're all already familiar with this. If you go, do any of you have a black car or dark car? Yep. You ever touch it on a sunny day? Burn your hand? Yeah. That's photothermal conversion. It's taking those photons and it's turning it into heat, directly into heat. So that black pigment takes that energy, converts it into vibrational energy, and that's just lost as heat. And so you'll notice, this is a nice little YouTube video I stole, took some screenshots. They took an IR camera and they measured the surface temperature of a black car versus a white car on a really sunny day. And they notice here almost 50-degree difference. Yeah, almost a 50-degree difference between the surface temperature. That's because of photothermal conversion. That's just sunlight hitting the car, generating heat. And so we thought that was pretty neat. And maybe we can take advantage of this to get rid of plastic that we already have. And so whether or not the pigment is carbon black or something like that, that's what's being formulated into these plastics. That's what's giving them the black color. And it turns out if you shine light on this, it's going to get hot. If you shine enough light on it, you can actually cause it to depolymerize, do the pyrolysis mechanism, and convert into monomers. And so that's what we took advantage of. We found a bunch of black plastic. Again, you can find this anywhere, right? I have a bunch of samples up here. You can find lots of other sources. About 20% of all the plastic we have contains some type of black pigment, carbon black being the cheapest. And what we found is that we could mix it in with some of these polymer resins. So we took some PET. We've actually improved this to almost quantitative yield now. So we can get essentially what is the monomer back from mixing this carbon black with the plastic and shining light on it. Simply light, including sunlight. We've shown this for polystyrene. We've actually gotten this yield up a little bit higher. I'll show you that in a few seconds using sunlight. And this works really well for PLA. So PLA isn't one I've talked about very much, but it's sort of, it's kind of like PET. So it's a polyester. They're both polyesters. But PLA has a lot of great properties. It comes from a biorenewable source. It comes from lactide. And it's pretty benign in terms of the plastic itself and the lactide monomer. They're pretty safe for you. The problem is lactide is pretty expensive to make. And so chemical recycling, converting the plastic back into the monomer, is really the best way to recycle it and would be the way to increase our dependence on PLA. And it turns out we can do this almost quantitatively using our technology. I have a cool video for you. So we do all of the initial R&D in our lab using, oh yeah, cool. Using LEDs. So we can buy these LEDs off of Amazon. They're pretty intense. You can't look at them directly. They're brighter than like your Christmas lights or anything like that. But we do all of our initial R&D in the lab so we can see if the process works. And so what we have here is we took some polystyrene. We made some polystyrene in the lab. We mixed it in with some of this black powder. We put it in a little vial, and all we do is we shine light on it. And so what you're going to see is the light's going to turn on, and you're going to see the powder starts to bubble a little bit, and then you're going to see all this looks like steam form on the glass vial. And that's the monomer being formed, right? So as soon as we turn on the light, this is sped up. You can see how that really bubbled, and then all of this vapor, that's the monomer that's being generated, simply through visible light irradiation. Now compare this to the 750 degrees Fahrenheit I was talking about earlier versus just shining an LED on the stuff. I don't know, that seems a lot easier, and it seems a lot more energy efficient. So we're pretty excited about that. We show that this works on a bunch of post-consumer waste products. Basically anything that has carbon black works. There's obviously different efficiencies here, and we're definitely working to try and understand like what are the additives in this plastic that maybe impact the efficiency of the process. There's a lot more R&D to do here, but we're pretty excited that we can directly recycle these plastics simply by shining light on them. We don't even have to add anything to them. We can just shine light on them. Fortunately, not ambient room lighting and not ambient sunlight. So you don't have to worry about your plastic making monomer just under ambient sunlight. We do need higher intensity than that, but it is pretty easy to achieve that intensity if you want. And so that's what we did. And this is actually work that was done by Hannah in the back. What she did is she took essentially a magnifying glass outside in winter, so it was cold in Jersey, and she put a little bit of the black styrofoam in the bottom of a vial. She focused the sunlight down to a point, and she found that she could recycle 80% of it back to monomer. So for context, existing pyrolysis technology, if you get 50%, you're doing pretty well. She could do an 80%, 5 minutes, using sunlight. So no energy input. All she had to do was cut up the plastic a little bit, and honestly, that's just so we could do it on our scale. And the great thing is, you may be asking, like, okay, this works on black plastic. What about all this other stuff I have up here, right? Turns out you can mix them together. The beautiful thing about the black dye is it doesn't do anything except convert light into heat. It doesn't decompose. It just sits there. It's essentially charcoal. That's basically what it is. And so when you shine light on it, it recycles all the plastic around it, and then it can move over and recycle the rest of the plastic that doesn't have the black dye. So it just needs to have some connection with the plastic. You can recycle mixtures of the two. And she shows us even better. We mix in a bunch of different types of polystyrene plastic, and using sunlight, you can recycle almost 70% of it, which is pretty cool. And then here's just another video. So this is what the sunlight, this is sped up, not quite as fast as the other one, but essentially as soon as the sunlight hits it, it starts pyrolyzing it, you start getting monomer. It's incredibly fast.
That's sunlight?
Yeah, that's focused sunlight.
But that's time lapse.
It was, yep. This is a 5-minute total experiment, so 30 times speed. Very fast. And honestly, I think it's because you didn't rotate it in this case, but oftentimes you do have to rotate it just to make sure that the light hits it, because it's focused to a very fine point. And so this is obviously on small scale, we're using a magnifying glass, but there are large scale solar focusing technology that already exists. And so there is a way to do this on scale. And then just the last little story I'm going to tell you. PVC, I haven't talked about PVC at all. You all know PVC, you have it in your pipes, right? It's the third most produced plastic that we have, and it is not recycled in any way, other than reusing. And so what Hanning, and this was all Hanning's idea, question, is if we could mix polystyrene and PVC together and make even more new products from it. So again, it uses the rubber ducky, was one of the casualties of our experiments. We have more of them now, so that's okay. But the challenge with PVC is, if you're familiar with chemistry or not, it has all of these chlorine bonds in it. So you may have heard of chlorine, like molecular chlorine you may use to purify your pool, or you use bromine, something like that. That molecule or that atom is found in PVC. And it's part of what gives it the great properties that it has. It's perfectly safe in PVC piping. The problem is when you try and recycle it, and if we use pyrolysis, it starts to generate HCl. Anybody know what HCl is? It's an acid. It's a really nasty acid. Muriatic acid, you may have heard that. You can buy it, right? Very corrosive. So you imagine a lot of these reactors are made out of metal. All of a sudden you get a little bit of PVC in there. All of a sudden you have HCl corroding everything, and it's a huge mess. PVC is kryptonite to plastics recycling. You cannot get it into your recycling stream, or you will contaminate the entire process. No one can recycle PVC. Yeah, muriatic acid, this is what it makes. So not great. Very corrosive, very dangerous. And so what Hanning did is she took styrofoam, she took PVC pipe, she took a little of our black, magic dust with sunlight or with our LEDs, and she could make, what happened? The styrene monomer, which you can buy, and the muriatic acid. And when these two mix together, you get a new chemical. You get a new commodity chemical. And that can be further derivatized into other things, like actually could be made into pharmaceuticals, or it could be made, again, into fragrances. You make more Chanel No. 5. That's how you make the money, right? You make Chanel No. 5. Turn plastic into Chanel No. 5. That's what we're trying to do, honestly. So this is great, right? We can take stuff that is essentially worthless, dirt cheap, and turn it into these high-value products just using a little bit of light and a little bit of our black magic dust. And so this works on PVC plastic. We can use styrene out of a bottle. We showed that this works really well. And again, it works on post-consumer waste. So these are just 8 different samples that Hanning found. PVC pipes, which I'm sure you're all familiar with. This is some packaging that some of our lab equipment or lab supplies came in, so we get to recycle those. Some of our gloves. We use tubing a lot in our lab. Someone had an old credit card. It's made out of PVC. A hotel card. A little ducky was sacrificed for one experiment. And then, I forget what this is. Huh? Construction piping. They were doing a lot of construction around the lab. We're like, all right, we're going to take that little piece and we're going to see if we can recycle it. And this is, we're really excited about this because PVC is not recycled, and here we are turning it into a high-value product, which is not showing up here, simply by mixing these two things together and shining a little bit of light in with our plastic, with our little magic black dust. And so that's all the research I want to tell you about, and the story I was going to tell you today. This is my research group. It's sort of an older photo. These are the people who do all the work. I just kind of sit there on the side and be like, yeah, sounds like a good idea. I kind of help them out and apply for funding. So we have a lot of government funding currently, hoping that stays that way, to help fund our research, because without that, the students don't have any funding to do their research. And so we need this to really try and keep developing these fundamental solutions. These are not obviously commercial strategies yet, but this is where it starts in the research lab, and we hope to try and develop these into prototypes, into commercial processes, so we can actually start recycling this stuff. And again, using sunlight, we're trying to use the most basic practical approaches you can to try and make this as cost effective as possible. So what can you do at home? Hopefully you learned some new things tonight. But this recycling RIC code, even though it's kind of crap, is still valid, right? Reduce, reuse, recycle. Recycle what you can. Know what is recyclable in your community, in your county. Only put those things in the recycling bin so that you don't contaminate it with other waste that can't be recycled. Try and reduce as much as possible, and try to focus on those plastics that are recyclable. Like maybe when you're going to the store, if you don't really have a preference for brand, perhaps you choose one that is using more recyclable packaging. So if it's using PET, that's a good thing, because PET is the most recycled plastic that we have. And it's recycled here, which is great. And reuse. So there's lots of creative solutions, and certainly with the internet these days, right? There's lots of stuff out there you can learn. People's ideas for trying to reuse some of these bottles if they're not recyclable in really creative ways. You can make this little sprinkler system here instead of buying something else, or you can make these little plants. I use these to start growing my little seedlings in the spring, right? I take some of these water bottles and stuff and just cut them up and start growing it in there. You just poke some holes in it. It does the same thing as the containers you can buy at Home Depot. So avoid single-use plastics when possible. Eco-friendly packaging, they can slap that on anything. It doesn't necessarily mean it is. You can try and do some research to see if the company is reputable and what their source is. But just because it says eco-friendly doesn't necessarily mean it is. And yeah, that's sort of all I have. So if you have any other questions.